Hello, everybody. Welcome to the new Daydream workshop, where we feature interesting research work and work from creative technologists in the real-time video AI space and autoregressive video models and world models, all the cutting edge and fun stuff happening in creative AI. My name is Eric Tang, and I'm the co-founder and CTO at Daydream. And today we have a super exciting workshop for you by the author of MotionStream, Joonghuk. He is currently in Pittsburgh doing work at Carnegie Mellon, and he's from Seoul, Korea. So I'm super excited to have him here. Before we dive into the workshop, I just want to, for those of you who are new in the audience, I just want to share a little bit about Daydream. Daydream is a community hub for real-time video AI and world models. We do a lot of open source work in this space, really to feature the work that the community is doing. For example, in the last year, we've done a lot of work to improve upon stream diffusion and make that work much better. So if you quickly look at this community hub, you will see all the interesting projects that the community has been doing and sharing in this place. A lot of it is touch designer because stream diffusion is kind of a really popular thing in the touch designer world, as well as this new tool called Scope that we have created. Scope is a tool for running these autoregressive models locally on your local GPU, and you can also deploy it in a cloud GPU service like a run pod or something like that. Right, so here you're seeing video being generated in real time and being recorded into a timeline, and that can, for example, can be shared with friends and things like that. So that's a little bit about Daydream. Another thing I want to share is kind of why real-time video and autoregressive models are interesting, I think, as a foreshadow for today's workshop. So here you're looking at a video being generated in real time using another model called LongLive, which is from NVIDIA, and this is open weight model that anyone can go and download. And I'm generating this first scene, which is a panning shot of a factory. Now I can paste in a new prompt and immediately see that scene change. Right now, the factory explodes. Right, I can paste in a new prompt, and and it generates in real time. Now, now there is a rainstorm that comes down. Right, so this really represents kind of a new way to do video creation. Another interesting thing is, you see what I just did here is I exported this timeline, which is just a JSON file. And I shared it with somebody else. Somebody else now can load this and generate the exact same video in real time because it's using the same seed and the same configuration. And they can now start to remix this video and say, hey, I don't like the third scene. Actually, what I want to do is I want to have an earthquake that happens right after this explosion, right? And you see that, now all of a sudden, an earthquake happens. I think this is a little taste for what autoregressive models can do for the creative process. This is a brave new world, so lots of innovations happening. And today we have one of the most popular papers in recent months, MotionStream, that's coming. So I'm really excited to be introducing Joonghuk to the stage.
Hello. It's good to see everybody, and thanks, Eric, for hosting this workshop. Yeah, if you guys have questions, you can scan the QR code. Yeah, and maybe Eric can deliver that questions for me. Yeah.
Yes, for sure. So for those who are new to the stream, we have this QR code on the top left. It will take you to the Daydream Discord, and in the Discord there's a channel called Sleepwalking. And people are watching there and asking questions in real time. So if you want to participate in the Q&A, jump in there and ask questions. And we'll have the presentation for about 30 minutes, and then we'll dive into the Q&A session. Sorry, I forgot to talk about the structure of today's talk. Thank you for reminding me, Joonghuk.
Okay, yep, and let's begin. Today I'm going to present a paper called MotionStream, Real-Time Video Generation with Interactive Motion Controls. And this work was done when I was doing an internship at Adobe with a professor from Carnegie Mellon University and my advisor from Seoul National University. So, a brief introduction about myself. I'm a first year PhD student from Seoul National University. I'm currently visiting CMU, as Eric mentioned. I did a project for this during internship at Adobe, and now I'm interested in building fast and interactive visual generative models. And more recently, I'm building physically accurate work models. Yeah, and I just wanted to give you a short backgrounds why I've got into this kind of drag-based stuff. I previously done a work called instant drag, where this is like an image model. You would drag points and you would make things bigger or smaller. It was published in SIGGRAPH Asia 2024, but yeah, it's a bit outdated these days. But yeah, this was where all my interest in this kind of like dragging and controlling things with motion cues all began. And now let's move on to the presentation part. Yeah, today, these days, word is hype about text to video or word models. We have OpenAI Sora, open source video models like One, or Google's really good model Veo or Genie 3. And another, like in academia, there are a shift in few step and autoregressive video diffusion models. The first paper that introduced the concept of causal generation is a paper called CosVid. What they do is instead of generating entire video sequence at a time, they generate a chunk by chunk. They call it autoregressively. And this work was published in this year's CVPR. And then there's a recent really famous work called Self-Forcing from my mentor during Adobe, Shun. This paper addresses the exposure issue from CosVid by training with the inference time simulated distribution. So yeah, this is a demo of the CosVid. You put a lot of prompts, and you can see the videos generating online with the streaming fashion. So you don't have to wait for entire time to videos to be generated. You can basically stream generate it. But there's a big issue with this kind of streaming-based video generation. This is a naive implementation of self-forcing with the motion conditions that I designed myself. As you can see, I'm accelerating over the time so that it doesn't get too long, but you see exposure is getting really bad over time, and there are a lot of artifacts happening. And after like something like 1 minute video, the person turns to somebody that we barely notice that this is the same person. So naive use of self-forcing results in a quick drifting because self-forcing was not meant to be used with beyond the teacher's training horizon, which is 81 frames, roughly 5 seconds. And because self-forcing has inconsistent speed, it has an attention context that is growing over time. And because the attention context changes over time, we are not getting a consistent throughput. Like we're not getting 16 FPS over time. We're getting it changed over time. And additionally, we don't, of course, have interactive controls. So one might even ask, like, why does a T2V model for 81 frames that's only like 5 seconds has to be AR? It could be bidirectional also. So I thought we need to have like a good streaming experience with some interactive controls. That's where it all began. And on the other line of this community, there has been a lot of work trying to condition the diffusion models, video diffusion models with motion conditions. One is Daniel Gang's motion prompting paper in this year's CVPR. They can do this basically. They can do camera controls, they can control the objects or the background. They do it with motion tracks, which is dense point trajectories. And another work is from Burgert. It's called Go with the Flow. You first generate a rough optical flow and condition the diffusion model on this rough optical flow. And you can also do a similar, like motion conditioning stuff like this. Yeah, but they have also a few limitations. The first one is they are really slow. So motion prompting, they're based on Google's closed source model called Lumiere. And they take 12 minutes to generate 5-second video. And of course, they do non-causal processing. So users have to put every input motion condition up front before the beginning. And they have to wait basically for like 10 minutes because they process every input motion at once. And because of this, they are limited in length. They're typically up to 5 seconds or 81 frames. Yeah, and we want to make this thing called really interactive, where users can continuously input prompts and videos are generated on the fly. So combining everything, this is a demo of ours, and I see a lot of people have probably watched it. You can drag things in the video, and the videos are generated on the fly, being conditioned by the static tracks. And most importantly, it lasts for significantly long duration. And yeah, with a little bit of engineering tweaks, you can add a static point, designating the points that should not move during the video generation with this kind of red dots. And the green dots are the points that are moving. You can fix all the point except for the nodes that you're dragging. And then you can also kind of like add more static points and um, raise the dog's hand like this, dog's arm. Or you could add additional static points and continue the editing part. Yeah. So this can not only be seen as a video generation, but it can be also used for image editing, like motion conditioned real-time image editing. In fact, this is much faster than a lot of image drag-based image editing works concurrently. So moving on, here's the key features of MotionStream. We offer super intuitive controls, which is basically drags. We have very fast speed, which is almost 30 FPS on a single A100 GPU, which is fastest among concurrent works. We do causal processing and accept conditions on the fly, so the users don't have to input all the condition motions and wait for like 10 minutes. And we can do infinite length streaming with minimal performance degradation. So here's the overview. We'll first talk about how to choose a good motion representation, how to prepare data, how we train the teacher model, and how we distill it in with to make it real time and causal. How we made it even faster with efficient VAE decoder and some evaluation, more demos, and I will talk about the questions and future directions and stuff. And first, let's move on to how to choose a good motion representation. There are many different ways to represent motions, and one is bounding box or blobs. So in a paper called Trailblazer, the authors try to condition the video model on the blobs like this. So yeah, they can basically give a rough blob, or in a paper called Blob.vid, they actually provide a blob instead of the bounding box. So there are pros and cons of this. Things are easy to annotate, but the problem is if you can only control things via bounding box, you cannot control the very details, the fine details. So you cannot, for instance, probably like move somebody's hair or probably change somebody's emotion and stuff, because everything's are very subtle, but it's very intuitive. Yeah. Another way of conditioning is sparse motion trajectories. You can try to condition the model on sparse point trajectories, which is typically about 1 to like 5 or 10 point. So yeah, there are papers called Motion Control and one ATI. Yeah, as you can see in these works, they typically train their model on really sparse set of trajectories. But again, this has an issue because with super sparse set of trajectories, you're sometimes not able to condition to change the background in a fine-grained detail or do the motion transfer and stuff. And when you want to do it super accurate, you can also condition the video diffusion models on the optical flow, where optical flow is basically a per pixel displacement between the frames. And the good thing about this is you can control with extremely fine details. You can even control every in a pixel level. But the problem is you might be able to generate videos on the fly real time, but you won't be able to provide this dense optical flow real time because humans cannot draw this kind of per pixel displacements for every like 16 FPS or something. So we wanted to make something like a good motion representation that can, that have good that has good interactivity and has a diverse use cases. So the thing that we use at the end is dense point trajectories, which is introduced by a recent paper, Motion Prompting and Diffusion as Shader. What they do is they condition the diffusion model on dense set of motion point trajectories, And then because you randomly sample the point trajectories during the training, the model sees different combination of point trajectories during the training. It could be dense, it could be sparse, it could be different type of point trajectories. The model naturally learns to adapt to different types of controls at the inference time. As you can see, if you train the model on different types of like dense point trajectories, you can expect it to be generalized to this kind of motion control. You can control with a bit more geometry aware stuff. You can even do camera controls. You can do both at the same time. And you can even do these kind of cool motion transfer, which requires a very dense understanding of the motion. And with a single motion representation, we can do these kind of diverse stuff. So yeah, that's why we decided to use dense point trajectories as our primary motion representation. And preparing the data is relatively straightforward. We need to get a point trajectories to condition our diffusion models on. And because we wanted to open source everything from the beginning, we try to use open video datasets, which are OpenVid 1 million, and some synthetic videos generated by larger one variant, meaning 114 billion. We did a bit of filtering because open source video datasets are typically very noisy. We did it primarily by video resolution and video length. And then we did point tracking with Code Tracker 3. So yeah, they allow us to track points like this. And then let's take a look at short architecture. So a lot of you guys will be familiar with control nets. So what motion prompting did is they first assigned a track with sinusoidal embedding. You can think of it as an identifier to each of the point trajectory, so that point trajectory maintains the identity throughout the generation period. And then they send it through a track head, a control net, and that's conditioned to the main diffusion transformer. And another way of doing this condition is actually encoding the point trajectories into an RGB video. So imagine you have a moving camera, and you can probably project it into a camera and make it, yeah, in an RGB video like this. And you can send it through a causal VAE that is typically used in video generation pipeline and send it through control net and do the exact same thing as motion prompting. So yeah, when you actually try to like visualize how they look, this is how they look. Sinusoidal positional embedding tend to have slightly more discrete representation, while RGB plus VA encoding kind of results in more dense. There are pros and cons, but yeah, they share a bit of limitation at the same time, which is that both of them are based on control net, which doubles the flops. So basically, control net is copy and pasting the earlier blocks of DIT and yeah, adding additional layers for it. So it doubles the flops. And because even if we distill it to 1 or 2 or 3 or 4 step, if we use control net, they will still impose the architectural bottleneck, which will make our model run twice as slower. So we thought that we had to use a simpler operation like channel-wise concatenation. And another thing to mention is the track head here is much more efficient than the causal VAE. And because again, we don't want to make our architecture bottleneck the entire system, we decided to use this learnable track head instead of using a causal VAE, because causal VAE, as you probably like seen, encoding videos are not really real time. Yep, and at the end, we designed a efficient positional embedding plus learnable track head based track conditioning mechanism. If you use that, time is like 50 times faster, and the results are probably like a bit more accurate. And this is how our teacher pipeline looks like. We have a bunch of like video data sets here. And from this video data set, we usually sample 1,000 to 2.5K tracks, assign each tracks a sinusoidal positional embedding, which becomes like an identifier for each of the tracks. We send it through the track head, and we obtain a track embedding at the end. And instead of using control net, we simply do a channel-wise concatenation with the video latents here and send it through the diffusion transformer to apply the final diffusion loss for fine-tuning. So this way we can train the DIT, and this DIT is based on 1.2.1 or 1.2.2. Dataset, as mentioned, is OpenVid 1 million plus 30 to 70K synthetic videos. Yeah, and to just give you how the tracks look like, if we randomly sample 1,000 or 100 sample pairs, it usually looks this way. Yeah. So one thing to notice is as videos go over time and progress, some of the points become invisible. So as you can see, a lot of things go out of the frame from the first frame, and at the end of like several seconds, basically nothing is left on the point trajectory. And this kind of makes the point trajectory condition diffusion models to be trained on longer sequences because conditions basically become very difficult to make it informative cues. So what we did at the end is to how do we actually more thought about how can we think of a way to train a diffusion model on a short sequence and make it generalized to longer sequence because we can't get longer and stable motion trajectories. Yep. And before moving on to the distillation part, I'll slightly and briefly introduce the text and motion conditions and how to use them during the inference time. So because our model accepts basically two conditions, which is text and another one is motion, at the inference time, you can do a technique called classify free guidance on these two domains. And when you only condition the diffusion model on the text prompts, we slightly find the result to be blurry sometimes. As you can see, it's not as clear as simply giving the motion condition. Another problem is when we only apply the motion condition, the problem is the video is generated following the motion tracks, but it follows it too well. So at the inference time, users cannot really provide a complex motion trajectories. For instance, they cannot give each point in a visibility or change the grid's spacing or something. At best, what users can provide during the inference time is like flat grid movements like this. And if every point in this grid is visible throughout the generation, the only corresponding motion would be translation like this. But we want something that is more complex, like this. So we combine the best of these two by mixing these two. So if you jointly guide it with motion condition and prompt, you would get the benefits of both too. So you can kind of like generate the videos with the natural video-based diffusion models like 2D dynamics, inheriting from prompt guidance, and you can do, and your videos will more accurately follow the motion conditions because you also have the motion condition. And moving on to the distillation part. So what we try to do is we want to get a long video generation capability with a constant speed, meaning constant throughput and constant latency. So what we observed is we try to visualize what tokens, what frames attend to what frames and what previous ones. So obviously, what we found is we found weirdly high attention signal to the initial frame here. And otherwise, the tension maps are pretty much diagonal. And this kind of motivates us to this solution, which is basically we always keep the initial frame, and we call it attention sync. It's quite common in LLMs. We call it sync token and keep it forever, and use a sliding window with a really short context so that the model does not have to keep all the history, but only the first chunk and the most recent chunk, so that we're basically keeping the attention context fixed at size of like 3 or 5. So throughput, latency, speed, everything is constant without a loss of significant quality degradation. And this is how our distillation pipeline works. So this is a bit technical, so I'll try to make it short. So during the self-forcing type of distillation, what we have to do is we have to simulate the inference time distribution. So how we do that is we kind of auto-regressively unroll the student generator and obtain a 81, probably like 81 frames, which is the teacher's training horizon, and ask the fake critic and the real teacher model to judge how realistic it looks. And then based on the discrepancy of these two, I mean, this is basically the like subtracting the real distribution minus fake distribution. And then using this gradient, we update the student model. This is how DMD works, distribution matching distillation. The key thing that differs our distillation framework compared to self-forcing is that we explicitly try to simulate the extrapolation like process during the inference time. And how we do it is we simulate the rolling KV cache and attention sync during the training. So imagine you have yeah, first, second, and third chunk, and then you want to generate the fourth chunk. So what self-forcing would typically do is they would simply add the fourth chunk until the KV cache gets full. But what we do is instead of yeah, naively adding the fourth cache, we omit the second one because this is not the first sync token and not the most recent one. So we just take this one out and we input the fourth token into the KV cache. And again, we do the similar things. And we call that rolling KV cache with attention sync during the training time. So it kind of allows us to explicitly simulate the extrapolation distributions during the training. So during the inference time, we can follow the exact same thing. Instead of keeping the histories, we just omit them out. And the KV caches never get longer than 3 chunks. So every extrapolation scenario is inside the distribution of training. And yeah, things are much better in quality overall. There are a bit of engineering tricks, which is rope. We assign the rope based on KV cache's position rather than the actual temporal index because their positions actually change over time, and we don't want the the temporal indexes to be assigned by something else. When we have a fixed size of KV cache, we use a chunk size of 3, meaning that we generate 3 latent tokens at a time. We adopt a 3-step distillation. And yeah, like we mentioned, we only use synthetic videos for this distillation because we tend to find that distillation training kind of converges really quick, and we don't really need that much of open with 1 million videos. Yeah, and that's pretty much it for distillation part. And actually, there's a cool observation, which is that so a natural hyperparameter resulting from this kind of framework is that how many tokens that we have to sync and how much history that we have to carry on. And left side is an ablation result. It shows the impact of the sync token size. And for this experiment, we set the local window size to 1, meaning that we only take the most recent history chunk in the KV cache. And the thing is, having a single sync token fixed is very important to mitigate the drifting, but having additional ones don't really help. It just increases the computational cost, and the output, the return is not that big. And on the other hand, we can also think about how many histories to contain and carry on over time. So in this case, we set the sync size as 1, meaning that we only keep the initial tokens in front. And here the interesting thing is, over time, keeping longer histories, like 5 chunks, do not actually help. Keeping a shorter history is even more helpful in most cases. Yeah, so here's the summary. At least having 1 sync chunk is crucial, but sync size over 1 doesn't really help them much, and it's much better to have a smaller local window size. Yeah, and how to make it even faster with tiny VAE. So if you use causal VAE, it usually becomes a significant bottleneck. So for instance, in 1.2.1, 1.3 billion, 47% of chunk generation wall time is spent in simply latent decoding. And for 1.2.2, 35% of chunk generation wall time is spent in decoding. And it means that even if you make it 2-step or even like single-step generation, you will be still bottlenecked a lot by the VAE. So there's a relevant project by open source called Made by Olin. It uses a much smaller VAE design with convnets. They have pretty bad performance. They show performance drop quite a bit, but they're still very fast. Yeah, and sometimes it's not really noticeable if you only use relatively simple motions or slow motions. And the way they train is they train by simply regressing the output of 1 VAE using an adversarial loss using patching discriminator, and the reconstruction loss with a replay buffer from GAN papers. So we did a similar thing. We keep the same architecture for 1.2.1, but with much better loss designs and larger data sets so that we get better LPIPs overall. So perceptual similarity is very close to the original video. And we design our own for 1.2.2. We find that simply adopting very small VAE decoder did not really work well for 1.2.2. So we had to make it slightly bigger than 1.2.1. But yeah, it was still pretty fast. As you can see, original decoder takes more than like, it takes almost 2 seconds, but our takes still like 0.2 second, which is much faster. Um, yeah, and the important thing is when you actually evaluate tiny VAEs in streaming generation setup, so the metrics that you have just seen before is the metrics using a GT video, but if you apply them in a streaming generation setup, because generation already contains some of the degraded artifacts or some kind of like, it's not pixel-wise perfect. So the impact of changing the full VAE to fast tiny VAEs is very negligible and it's hardly noticeable. So as you can see, latency gets almost halved and throughput gets almost doubled, but the PSNR, LPIPs, and SSIM, they look all similar, and I would say they are very negligible in terms of performance. So it's same for 1.2.2 baselines. Speed gets more than doubled here, but the performance remains very consistent. Yeah. And moving on, evaluation. I will not go into the details, but basically our method does pretty well with motion reconstruction and motion transfer tasks compared to previous state-of-the-art model, despite being like 2 orders of magnitude faster. Surprisingly, our method can also do camera controls. We can first do the scene lifting with depth prediction. And based on that, we can get a point cloud, a rough point cloud, and move our camera in a designated trajectory, and then reproject those kind of points into the camera's plane to get the motion trajectories and their visibility. If you do that, we can get pretty much good novel view synthesis results as well. And here are a bit of limitations. So the first thing is that because our model has a fixed tension context, it means that we are doing a trade-off basically with a longer history and a shorter history with fixed context length. So our model has a limitation in terms of memory. So videos get longer and longer because they do not contain all of the history. They would sometimes forget things, and it's bad for word exploration tasks like this. And there's also inherent limitation in the motion trajectory, which is that it's hard to represent long-range trajectories. So as I mentioned, if you try to train it on the longer sequences with scene changes, they will usually result in almost no visible motion trajectories at the end. And because of that, the model faces difficulty when we try to generate longer sequence with longer tracks, because tracks are no longer visible in most of the time. And when none of the tracks are visible because of the attention sink effect, so as you can see, the video kind of like sometimes rolls back to the original scene, and that's the impact of attention sink. And another one is model's capacity issue. Because our model is trained on 1.3 billion, sometimes we can enforce the model to generate some kind of movements that the base model could not. So for instance, the base model, no matter how we prompt, it's really hard to hatch the turtle from an egg. But if you do motion condition, we can force it to make it go out of the egg. But the problem is, the results are sometimes not really natural or very, very good. So you see the turtle's legs still here. And because user inputs are basically imperfect at all times, you cannot really draw the natural and very, very point-wise accurate trajectories. We are always like expecting the model to generalize on these kind of imperfect tracks. So as time passes by and as these kind of errors on the motion condition accumulates, we get degraded results over time sometimes. So those are the limitations. But yeah, larger models tend to have like better generalizability. So yeah, by extending this to 14 billion or something that is better, or a compact model that has better performance, I think we can expect it to generalize better. Then let's talk about a few downstream tasks that we can do with this. So one thing that you can do is, yeah, like zooming in. So we added a feature like you can add multiple tracks before start streaming like this, and you can even do something like this. Yeah. So all of these are raw screen recordings without any acceleration or stuff. Um, you could do some fun stuff. You can try to fix the mammoth in this kind of position and only drag the background so that mammoth can do some kind of like moonwork here. So yeah, it's really cool how video diffusion model generates this kind of like, yeah, snows coming from the mammoth over time. Uh, yep. And you can also designate several balloons trajectories up front because we only have a single mouse. We cannot control multiple objects at the same time. So you can, yeah, predefine some other balloons trajectories. And for the big balloon object on our focus, we can control it. And the other ones will move following this kind of trajectories. And we can control ours with the online trajectory, yeah, that we input. Yep. So yeah, this is pretty much it. You can basically do some other things. So this is the camera control results. Because our model is based on a actual, yeah, physically 3D aware point clouds. Good thing is that model does not hallucinate motions or camera motions. It's really accurate in a lot of times, and I think that is the reason why our model does pretty well with novel view synthesis task. Yeah, you can do dolly zoom like this. You can do the camera controls with like predefined camera trajectories. You can also do motion transfer. A good thing is that because our model does really well with the long video sequence that is tied to an initial scene, it is really good for like online video to video translation. And especially when you use online tracker that is accurate, you no longer have to draw it with your hands, and that makes things more accurate. And you can do this for a really long period of time. And if you somehow can get a trajectory like this, you can also convert it to, yeah, um, in a different scene, do motion transfer, change a guy into a Santa Claus with human key point trackers. Please note that these kind of like point tracking stuff in specified and less domain and smaller domains can run real time. Yep, and that's pretty much it. More of the future directions could include reducing the latency further. Currently, the model is real quick. It's, I would say, responsive, but when we try to run on like local devices, like maybe like 4060 or something, it will have longer latency, and that will kind of make controlling things a bit more difficult. And we have to have a better distillation method that can prevent the quality degradation from imperfect users drag queues instead of the GT drag queues. And going toward word models, I think there is inherent trade-off how to make in making it more interactive or physically accurate with longer memories. But yeah, these are ongoing research areas, and I think yeah, a lot of community efforts will be held in this, making it more physically accurate while maintaining the interactivity next year. So yeah, that's a good part to work on. Yeah, and that's it for today's presentation. And yeah, you can feel free to make questions if you have any. Yep.
Well, thank you, Joonghuk, for an awesome presentation. I feel like this is like three papers in one. You did so many different things in sequence that I really accumulated into something that's really cool. Um, so I, so for those who are watching on YouTube or other places, if you want to ask questions, you can scan the QR code on the top left, which will take you into the Daydream Discord, and we will be monitoring the questions there. There's a voice channel that's active right now, and people are already in there asking questions. So I'll play MC here and ask Joonghuk some questions that's from the audience. First one, I see this in the audience here. Um, Do you think the motion trajectory representation and the ability to derive the trajectories using depth data kind of obviates the need to directly include the depth data as the conditioning in the model?
Um, we did not really consider directly using the depth as a condition, but that is for sure a good way of integrating depth conditions if we want to condition the diffusion model based on accurate depth. But there are a bit of downsides for it. You're actually giving up some of the interactivity, so you cannot really generate depth map on the fly. So we kind of wanted to make things controllable with user mouse.
Mm.
So that's the reason why we didn't do it. But yeah, if you're trying to do depth condition video to video translation, so that you have accurate depth of something and you want to translate it, like directly conditioning the depth to the video diffusion model will be a good thing too.
Yeah, I can imagine if it's something like a style transfer,
Hmm.
right? And then you'd be able to like use one camera input and kind of do the other input. That may be an interesting way to explore. I wonder how this would perform compared to the other papers like Stream Diffusion V2 and things like that.
Hmm.
Um, yeah, so there's a few other questions. I'll get to them second. Um, is there a oh, hello? Um,
Yeah.
hold on here. All right, give me one second. There's some feedback that's happening. Um, okay. How did you decide to train the motion condition directly into the model instead of using the control net type approach? I know you talked about at the beginning of the paper. Did you like try the control nets first and then realize that hey, it wasn't working so well? We got to find other ways to do the control.
So I did control net. I did try control net because control net offers several advantages. So the biggest thing about control net is that training has a guaranteed lower bound because we initialize it with zero convolution and stuff. Or in DIT, we initialize with zero linear. We can maintain the base model's performance. So I first tried with ControlNet, got pretty good results, but it wasn't really fast. And we found out that the teacher model typically takes like 5 minutes to generate 5 second sequence. But if it's ControlNet, it gets like 8 or 9 minutes. So yeah, we thought it would be less efficient for doing things online. So that's the reason why I did not use ControlNets. And I think ControlNets is actually could be better because we're actually using a lot more parameters for it, and we're going to get much more stable training. But if we somehow can get it converged, I think the performance should be similar. So yeah, we have a better, I think, combination. We have pretty similar performance at much faster speed. So yeah.
I see. Yeah, that's interesting. So it sounds like a just a big speed optimization, and that's why
Mhm.
you kind of went the other way. Um, I'm curious if you were thinking about training the like on the bigger base models, right? Like a
Mhm.
14B model or something like that. Like, how would you do this differently?
So training 14 billion model with self-forcing is already quite challenging. You have to do a lot of tricks to do the KV caching and stuff. So control that would not be, is going to be even more difficult for a 14 billion one. So I'll probably stick with Kirin approach, but I'll have to make a lot of engineering tricks to make it fit. So there's a work from Crea 14 billion, that one. They did a lot of engineering tricks regarding the KV cache. We can also do some context parallel thing during the training, like sequence parallel, ring attention and stuff. Um, yeah, but overall, I don't think things have to be changed that much to apply to larger models. We just have to do a bit more engineering to make it fit into the memory and do some gradient truncation trick, clever ones from following the Crea. Yeah, that should be the recipe probably.
Interesting. Right, yeah, because this is like when you're training, when you're doing the training, like managing the memory and optimizing for all of that. Like, so it doesn't, so like fits in the VRAM when you're doing the training, right?
Right.
Yeah. Um, yeah, like another question. Um, people want to, people want to know where to best follow your research work. I'd assume you're working on new projects right now.
Oh, yeah. You can find me on my website, personal website. It's called Joonghuk.com. Um, I did several works on image editing, motion condition video or image generation, and I'm also planning to continue my work on yep, word models these days. I'm actually trying to generate a fast and interactive word models that can have longer memory and yeah, that we can kind of like use diffusion models more like a renderer instead of generating everything. We have a 3D representation. We try to use apply the autoregressive video diffusion models to render things real quick, make it more yeah fancy, real world like and stuff. Yep. So all of those works, I will continue working on it next year maybe. So you can follow up my webpage.
Yeah, that's very exciting direction. That's something that we've also seen a lot of experimentation on. People are building kind of interactive games using these kind of new models,
Mhm.
and a lot of times I think especially if you think about putting this kind of techniques into a game engine or a 3D world or something like that, being able to style transfer and kind of take a bare bones 3D world and put styles on it quickly using diffusion models and make it look nice is a
Mhm.
super powerful thing.
Yeah.
Yeah, so excited to see your new work here. Um, Another question from the audience: do you think that having a 3D prior is important in the area that you're working on, or are you kind of in this mindset of eventually the priors won't be as necessary?
I think in this stage, all of the big tech companies, including Google or some other cool companies like OpenAI, everything is getting embedded into a single very large model and very multi-model model. For instance, we know Nano Banana is good because they're embedded into Gemini, and Geminis can exploit a lot of internal knowledge from the LLMs. So Nano Banana or maybe VO4, whatever that comes out later, can actually be more physically accurate, benefiting from those kind of large language models. But in open source, we do not really have those kind of like big knowledge pool, right? So maybe somebody can build things on top of Coin 3, but that's going to require too much work. So I think one good way of having a good knowledge that we can based on to make it more physically accurate or give some helps is 3D features or some other tokens that we can refer to. But I think 3D token is basically very straightforward. We can give it a strong cue instead of making the model learn from very implicit tokens from the LLMs. And yeah, it's easy for academia to actually control the 3D features. We have diverse and really good 3D perceptive models. So I think building on top of that would be yeah a one promising direction in academia. But if you get to have a lot of compute and a lot of like really good LLMs, I think building on top of it and using that prior knowledge could be another really good direction in the industry.
Mm. Right, taking some, yeah, in the open source world we can take some shortcuts. um,
Mhm.
yeah, for sure. um, Talking about shortcuts, people are curious to learn more about the training process. I know that you shared that in your talk, it takes between 30,000 videos and 70,000 videos
Uh-huh.
in this training run. I'm curious, that's like a pretty big range, right? Like, what's the trade-off between 30 and 70? Why is there a range?
Oh,
Uh,
okay.
and and yeah, like, and what was the training path like?
Oh, so actually, I was also an intern, so I didn't get to use bunch like hundreds of GPUs. So most of the training is conducted with 4 nodes, which is like 30 to 800 GPUs, and for 2 or 3 days. So it's not really impossible to re-implement it using a single node of H100 using like probably like 4 to 5 days similarly. So it's not really that computationally expensive, but the data. So I mentioned I used two set of data, which is OpenWidth 1 million and synthetic data. So, oh, for 30, I was supposed to say 30K. Maybe there's like
Right, yeah, yeah.
a bit of confusion here. But the reason why I use 30K and 70K is that there's actually a open source sampled video from repository called Fast Video Team. So they sampled and shared 30K and 70K synthetic videos for 1.2.1 and 1.2.2. So that is the reason it's called synthetic videos. I mean 30K to 70K. We use 30K for 1.2.1, maybe the opposite, 70K for 1.2.1 and 30K for 1.2.2 because the data set they shared is of that size.
Mm, What was your experience using that open source data set? It like what because when I talk to people who work on the model trainings, people always say, hey, the lowest hanging fruit is just get better training data.
Mhm.
That's always like the best way to make your model perform better overall. Um, yeah, curious, what if you've thought about the quality of the data, like if there's room for improvement on that side.
Um, for open source synthetic ones, they're really good because they're sampled from the video generation models that already capture the mode of the data distribution. They tend to be good and they tend to be sampled with pretty good prompts. So they're good. But yeah, for open source data sets, like real world data sets like OpenVid 1 million, you have to filter it carefully, I think, because they sometimes contain, um, I mean, it's called 1 million, but I would say like 10% of them could be sourced from an image instead of the video. And inside that image, they're just like zooming in, zooming out, moving toward different directions. So a lot of videos are really easy or it's not really informative. So you have to filter it carefully. But in general, I think even that noise can help you models to learn how things move and how camera should move, like or zooming in. So I showed a example of iguana, and that was probably possible because that OpenBit 1 million contained a lot of zooming in cases, so that we could learn more about how to zoom in. Yeah, but I would probably try to look for better data sets. And I see a lot of better data sets coming out. I haven't tried things that came after this thing. So yeah, it's also very interesting to see how open source data set gets better and better.
Mm, mm. Um, People asked, if it's possible um, to combine this type of motion control with other types of control mechanisms,
Mhm.
maybe style control using LoRa's or things like that.
Yeah, it should be possible. The reason why I did not train this model w- using LoRa is because using LoRa already adds some kind of adds a bit of latency and throughput bottleneck because you have to calculate LoRa, you have to multiply metrics more, and that kind of makes flash attention and stuff a bit more difficult. But if you slightly give up on the speed part, yeah, you could make entire thing into a LoRa, and then you would be able to yeah add things. That's I think how community did for self-forcing. I think they have LoRa for self-forcing and kind of combine things, but that kind of slows down the entire process a bit. Um, but for ours, I think yeah, when you try to condition the video diffusion models with drags, you actually feel really um, sensitive, even more sensitive about the latency. Because if you try to condition on the text prompt, it doesn't really matter when the things appear, when the things that you type in gets appear and gets reflected. But for dragging, like you don't really want things to be dragged um, like 1 second later. So probably having like zero point 0.2 or 0.3 second latency is the optimal that we can get. But using LoRa will kind of like make it go zero point 0.5 or zero point 0.6 seconds. So it's very noticeable.
Mm, I see. Interesting. Um, and so it's more like impacting on the latency rather than the frame rate, or do you think it this way?
Um, I would say latency is much more important in this for this work because people want responsiveness and latency and the throughput is not sometimes very important. So even for our work somehow at the end achieved 30 FPS, which is way faster than I expected. And making it have high throughput comes at a significant disadvantage, which is that things tend to yeah drift much quicker because our model is still trained on the short sequence and things eventually drift at the end. Um, yeah, if you try to run things faster, like 30 FPS, we will reach 1,000 frame much quicker, 5,000 frame much quicker, and yeah, things will drift quicker and things are more difficult to control. So I would say, yeah, I would prioritize the latency for sure.
That's good. Um, cool. So, by the way, how are you doing on time? We have a couple other questions from the audience.
I have a lot of time at the end, so we
Okay,
can slightly longer.
perfect. Perfect. Okay. So another question from the audience. The paper mentions that the model is trained based on the Wen 2.1, 1.3B I2B model,
Uh-huh.
but there's no official release for the
Right.
1.3B I2B model. Did you train a custom version yourself, or did you take a community version?
There's a version called One Fun from Alibaba. I simply grabbed their pre-trained weights and removed some of them because they're not really fit. That doesn't really fit my needs. So yeah, I used something similar to their architecture, removed some of it, and tweaked a bit to make it I2V. So it doesn't really work I2V for 1.3B, but yeah, we simply call that 2.1 I2V setup.
Got it. Got it. Cool. Um, okay. I think there was another question that was in the audience. Oh, I see. This was asking me about time. Um, cool. Last chance for people to ask questions. I'll give a couple more minutes. Um, I have I have a question myself, which is more related to there's some people in the audience that are building applications in this space. Um, obviously the demo, the demo experience that you guys had show this the possibility of this like dragging type of almost like image editing
Mhm.
workflow. Um, what are some of the other types of use cases or application level thoughts that you have come across either from yourself or in the work process or through the community that have shared their thoughts with you?
So yeah, one thing could be it doesn't have to be drag. It can be as long as it as a motion track can be sourced out of it. It can be any type of condition. So for instance, you can think of in VFX like you can have human motion capture and have human wear some kind of like a motion capture shoot, and you can source the condition from that, and that will be way more accurate because that's physically accurate one that's not drawn in. And if we condition on that, we will be able to generate longer sequence streaming. So maybe people can see the results. Maybe like yeah, directors can see the cool results on the fly on their camera as they capture stuff. Um, yeah, a lot of things that does not have to be that keeps that is aware of motion can be done with this. I think could be some other motion trajectory stuff. Could mouse is just simply one thing that we can show most easily, yeah, because it's very it's simple. So one thing that we can also consider is like touch interface. So because our model is also kept meant to be very fast and very compact, um, imagine this thing running on your iPhone and you have a human head and you can even do the multi-touch. You can you can hold their mouse together, make it big, open the mouth, close the mouth, and turn the heads. Um, and one thing that we observed also is that the one base model is kind of like memory heavy, but because we only contain very small attention, local attention window and attention context, the memory cap, the max memory peak coming from the entire model, if you don't count the T5 text encoder, which is already very like big, the pure memory consumption is like 5 or 6 gigabytes. So theoretically, if we only have the compute, we can run it for like, I guess like 4 to 5 FPS on an Mac maybe or an iPhone. So yeah, if we optimize it further using Apple's like own API or something, and we have better compute or better chips, I think that's also a very promising direction.
Mm, yeah, I think the local AI people will be very excited to hear this. Getting the smaller models
Mhm.
always super interesting. Um, okay, cool. Um, um, Lastly, let's like people. I don't know if you talked about this. People are wondering if the model is on open weight and ready to be downloaded.
Yeah, I forgot to discuss it during the talk. Yeah, I mean, I think as an intern, I originally thought it would be open source without any of the difficulties, but as things get viral, I think Adobe is taking more cautious approach to careful approach to handle this because people might be using it for different purposes, and Adobe wants to just make sure that everything is safe. And yeah, they have to also think about the company's business also. So I don't know what's happening exactly, but I'm always like, yeah, trying to ask them how can we get open source data or not. But it's the answer is not no for sure at this period. I haven't got any response yet because maybe we can find a better time to ask it. And so I think it could be and could not be open source both, but yeah, we haven't really got a concrete response yet. They said that's under review, and that's something that we cannot force even more. So
Hmm,
yeah, I
yeah,
will probably like try to make the last question and try to ask them mm, at maybe end of the year or early next year, so that at least people can try it. But yeah, I can't guarantee it will be open source, or
yeah,
I can't guarantee that it's not going to be open source both at the same time.
yes. I'm sure if it ends up not being open source, the paper's out there and people will be trying to replicate the work.
Yeah, I
Um,
think a lot of people are actually. I heard some efforts that are trying to reproduce the work, and yeah, it only takes like a single node of 800 and like 5 or 4 days to reproduce it. So if yeah, I think it shouldn't be too difficult as well.
hmm, cool. Um, Okay, some other questions coming in. Have you tried using higher resolution tracker like 100 by 100 that could potentially provide more precision control?
Uh, yeah, I tried it for my visualization purposes, but having the train model on it because the main reason is that um, it's about the speed and the memory consumption. If you want to track more points at the same time, it takes much more compute. So I think 50 times 50 was the pretty good point where we can balance both the quality and the speed.
Hmm,
Uh, you can track all the points, which would result in like 400K points for 2.1's resolution, but that's going to make things too slow. Yeah.
got it. Some other questions. What's your thought on the SAM3 pipeline and if that's gonna like if kind of some kind of segmentation
Mhm.
would be helpful either in the training or in the inference
Yeah.
stage?
I do think SAM3 pipeline is going to be very helpful. I didn't have that technology when I was doing an internship, but the biggest thing that I thought about during the training a teacher model is that sometimes some points are much more informative than the other ones. For instance, if we're turning a dog's head, I think the points like nose or some points on the edges are much more informative. And using SAM3, we can get a segmentation mask, and maybe we don't need it to sample the points from the background, for instance, which remains static. So we can provide the teacher model more informative tools if we have the segment masks. So yeah, and probably sample from the motion edges so that people will typically try to draw more on the edges, and we can enforce model to learn things better from it. That's going to be very helpful. Yep.
Yes. Cool. Let me see if there's any other questions that are in the audience. Cool. Okay. Sounds like uh, we are out of questions. Yeah, Joonghuk, thank you so much for this workshop. It's been really awesome and informative. Can't wait to hear your see your future work here. Would love to have you in the community and come back and revisit us at some point. For those who are in the audience, we are Daydream, and we are a community for real-time autoregressive models and mode models. Um, we are doing these kind of workshops, trying to do this every week, actually. So the next week, we will have a workshop specifically on Scope, which is a open source tool that allows you to really easily run these types of autoregressive models like Long Live and Stream Diffusion V2 and the Korea 14B model. We've actually done some quantization on the Korea 14B model to make it fit on a 5090, so people can run it on their consumer cards. And this tool, Scope, it allows you to really easily get those models set up and also experiment and build custom workflows on top. You can also build applications because it exposes this API. So we'll be doing that workshop next week. If you're interested,